So I thought just to finish this series we'd have a go at one of the bigger past paper questions on this. So as I mentioned in one of the videos, what they like to do is combine all the different spectra together, or maybe one or two of the spectra together, and give you a big, I think this one, so this one's worth 6 marks, there's one that's worth 10 marks elsewhere. I don't think I've got it here, but there's another one worth 10 marks elsewhere. We'll have a go at this one today. So it says, compound Y is a halogenoalkane, a simplified form of the infrared spectrum, the mass spectrum, the carbon-13 NMR spectrum, and the low-resolution proton NMR spectrum of Y are shown below. So we've got an infrared spectrum there. We can use the data booklet to work stuff out about that. We've got a mass spectrum there. We've got a carbon NMR and a proton NMR spectrum. Then it says, use these spectra to determine the identity of compound Y. You must use evidence from each spectrum and explain how you used it. So when you come up to a question like this, it's often a little bit daunting. You're a bit thinking, where on earth shall I start? I would, if I was you, you tend to do the same, well, I tend to do the same sort of things with it. I start with the spectrum that's easiest to interpret. So usually the infrared spectrum is the easiest to interpret. I then look at the molecular ion peak. So I don't look at the fragments. It's always really difficult to work out the fragments straight away. So infrared, then go to the mass spectrum and look at the molecular ion peak so we can get the MR. Then go to the NMR, see what you can get out of the NMR, and then if you still need some help working it, by then you should have really know what the molecule is, but if you don't, for some reason they've made it even more difficult, then you can start looking at the fragments. So infrared, molecular ion peak for the MR, then the NMR, and then the fragments. So that's what we'll do with this question. It works for pretty much any question. Let's imagine they didn't give you NMR. You just take NMR out and do the same order, but without looking at NMR. So first thing, let's look at the infrared spectrum. So it's going to be a little bit harder to squeeze it in, but this is the infrared spectrum here. I know it's a halogenoalkane, so if we get that piece of information down, halogenoalkane, so it's got a halogen in it. That there is CH bonds, so if we say, I'll have to just try and move this to the side there, that might work. Hang on, give me a second. Right, hopefully that's positioned so you can see most of it now. So I know it's a halogenoalkane. I know if I look in the data booklet that this peak here is going to be caused by a CH bond. So if I would set it out this way. So I do one, I'd start talking about infrared, and I'd say peak between 2000, what is it officially in the data booklet? 2,800 and 3,100 centimeters to the -1 is a CH peak, so caused by CH bonds. And then I'm looking for the peak, the halogen, the peak for the halogen. So there's a peak here which is at 650. So peak at 650 centimeters to the -1 is a carbon to chlorine bond. So that's caused by carbon to chlorine. If you look in the data booklet, 650 can only be carbon to chlorine. So now I know it's a chloroalkane. And I also know it hasn't got an alcohol in it or anything like that. It's just a simple halogenoalkane. It might have more than one chlorine in it, but it's a chloroalkane. I then look at the mass spectrum, and I would say the molecular ion peak so the molecular ion peak is, well, there's 3 of them in this case. So that is going to be caused by isotopes, which you'll have learned about in Unit 1. But if we just use the one with the highest number, so what's this going up in? twos. I'm going to say twos. 2, 4, 6, 8, 10. So molecular ion peak is 130. So the MR is therefore the MR equals 130. Now it depends how well you've done your revision, but if you look at the molecular ion peaks here, you can see that they're in a 9 to 6 to 1 ratio. And the only time you've ever seen something in a 9 to 6 to 1 ratio like that is when you've got two different chlorine atoms in your molecule. So that's kind of giving it away, but we can just try and work out what would give us 130. So you've got to start playing around now. I know I've got carbons in there, I know I've got hydrogens in there, and I know I've got chlorines in there. The ones that are causing the highest peak there are going to be the 37 chlorines, so this isotope here, and then the other ones are going to be maybe a combination of both, or the 37 chlorines. So if we can get somewhere around 130 as the MR, then we know we're on the right lines. So it's going to be a decent sized molecule. I'm not going to pretend I don't know that 9 to 6 to 1 ratio, so I'm going to say I've got 2 chlorines here. So 2 chlorine 37s, I got a calculator. So 37 times 2, that's going to be 74. So if I do 130 minus 74 now, I know 130 minus 74 is 56, so the rest of this thing here is going to have an MR of 56. So I'm going to guess 4 hydrogens, and that'll be 48, so 4 carbons, which 4 times 12 gives you 48, and then if I say 8 hydrogens, that's going to give me 56. So this is 48, and that is 8. So if I add 48 plus 8 plus 74, pretty sure it would give me, let's just check it, 130. So that gives me 130. So that is my molecule. In terms of what's causing the 9 to 6 to 1 ratio, you're going to have C4H8 and then 37Cl, where both of the chlorines are 37Cls. You're going to have another possible combination where you've got a 35Cl and a 37Cl, and then you'll have another combination where you've got C4H8 and 2 35Cls, like that. So that's why you get those 3 different peaks, because you've got those 3 potential molecular ions there. So I kind of know from the molecular ion peak what my molecule is starting to look like. I could probably start guessing actually and trying to draw that, but now I'm going to go stick to the routines, try and do the NMR. So if I look at the NMR spectrum, I'll start with carbon. I'm going to go very basic. I'm going to say there's 2, so carbon, 2 environments. I'm not even going to try and work out what the environments are, because I think I probably know from the molecule I've got. Carbon, there's 2 peaks, so 2 environments, and hydrogen, there's also 2 hydrogen environments. At this point now, I'm probably going to start trying to work out what my molecule actually, so 2 environments, because there's 2 peaks, and 2 environments here, because there's 2 peaks as well. At this point, now I'm going to start trying to think about what my molecule is. I haven't even thought about fragments. I'm not going to concern myself with that yet. I'll do that probably in retrospect. So, as I said, now we're going to try and use this information to work out what the molecule is. It's got to have carbon to hydrogen bonds, carbon to chlorine bonds, no other bonds in the molecule. It's got to have an MR of 130. It's got to have that chemical formula. It's got to have 2 carbon environments and 2 hydrogen environments. So start with the molecular formula. 4 carbons, I'll do the straight chain first. Let's do 2 chlorines there. So I've got to now decide, does this molecule work based on this criteria? It's got CH bonds, it's got CCl bonds, it fits this chemical formula. In terms of carbon environments, it would have 1, 2, 3, 4. So it can't be this one. It's same with hydrogen environments, it wouldn't work. So that doesn't work. If I maybe move the chlorines and do something like this. Let's do chlorine there. And let's do a chlorine there. So let's do it like that. This time, still good with the MR, still good with the bonds. Carbon environment, it's got 1, 2, so it's got the A's and the B's, so that works. Hydrogen environments, it would have this, well let's do X's, X, 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 Y, Y, Z, Z, Z. So that one works, that's got potential. And I think I could spot another one that works, so it could look like this as well. We flip the chlorines to the 1 and 4 positions, so that it looks like this. So I've got to find something that helps me to determine which of these two it would be, because they both fit my criteria so far. So these are X's, Y, 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 and Z, and X, X. So these two are in the same position environment. So these two are same as these two. So in this spectrum, we would have 2 carbon environments, 2 different peaks, both the same height. In this, 2 different carbon environments, 2 different peaks, both the same height. In the top one here, we're going to have, oh, I've called this Z, let's call that X. In the top one here, the HX's are going to be 6 high, because there's 6 of them, and the HY's are going to be 2 high, because there's 2 of them. In this one, the HX's are going to be 4 high, and the HY's are going to be 4 high. So if I look back at the carbon NMR spectrum, or not even the carbon NMR spectrum, sorry, the proton NMR spectrum, you can see that the 2 peaks are the same height. Actually, the molecule that works is going to be this one, and that one doesn't work. So this one's the one that works, 1,4-dichlorobutane, rather than this one, because you've got the same number of hydrogens in the environment. So 1,4-dichlorobutane is it compound Y? I'm going to call it compound Y. And then the final reasoning we need to talk about is the fact that it's got the same number of protons in both environments. So there's the same number of protons in the Y environment as there are in the X environment, therefore the peaks are the same height. I didn't need to use fragments to work out the molecule. You don't even need to use fragments to the mark scheme in this question, so we will leave it as that.